Good day everyone, my name is Norma Degdagan and together with my group mates Orlando Luis Bolaton and Justin Estuesta, we will be discussing and presenting to you our device called the Real-Time Pressure Sensing Seat Cushion for pediatric wheelchair using Atmega 328P. Here we have the revisions on our DESIGN2 and we have tabulated it to show you where we reflected in our paper and how we addressed it. Next, we have the needs. So there is the special class for these disabled children in which these students often ask their guardians to reposition them while sitting because they experience these pressure sores in which it cuts off their blood supply and in worst cases, it affects their muscles and their ligaments. So they need a device that lets them know when and where pressure is accumulated. Objectives. The main objective is to provide the disabled children of a pressure sensing seat cushion on a wheelchair that would indicate the pressure experienced in a sedentary position. Specific objectives. First, we have design a device that makes use of an Atmega 328P microcontroller to control the operation of the device, to create a pressure sensor matrix using pressure-sensitive conductive sheets, to provide the visualization tool for the user in diagnosing the areas of pressure with the use of the generated map, and lastly, to power the device with a portable battery to increase its mobility. Scopes and limitations: the user must be less than 9 years old and he or she must be weighing less than 30 kilograms, and the device is meant to inform the user when pressure accumulates. Next we have the conceptual framework. Our input: pressure sensor matrix values. The processes include the microcontroller reading multiplexer values, the HC06 Bluetooth module connecting to the phone via Bluetooth, and the notification for the user if 10 minutes has already passed. Next, we have an output, the visual representation of the pressure matrix to the phone via Bluetooth. Next, we have the hardware block diagram of our device. You can see that the pressure sensor matrix is connected to the multiplexer, which is connected to the microcontroller, which is connected to the Bluetooth module, which will be connected to the Android phone via Bluetooth. And you can also see that the multiplexer, the microcontroller, and the Bluetooth module are all powered by the 5 volts power supply on the power button. Next, we have the isometric model of our device. Here we have the isometric model of the controller of the device and the isometric model of the proposed design. Next, we have the program flow chart of the main module of the microcontroller. First, it initializes the Bluetooth connection. Next, it checks if the phone is connected to the device via Bluetooth, and if it's true, it proceeds to the module scan mat. Here we have the program flow chart of scan mat. First, it initializes row and call to 0. This ensures that the program starts at the topmost left box of the 15 by 15 matrix. Next, it checks if the row value is less than 15. And if it's true, it then asks if the column value is less than 15. If it's also true, we move on to the get point force module. Here we have the get point force module, row and call. First, it writes row and call to the multiplexer. Then the microcontroller will read value from the multiplexer. Then this value will be needed in calculating for the voltage, and once the voltage has been calculated, the program will calculate for the resistance. This resistance will be later then converted to force, and then this force value will be stored into a variable called point force, in which it will be returned into the ScanMat module and be placed into a variable called value. Now this value will be displayed to the device, and after displaying the value, the program will add 1 to the variable call, and you can imagine that it moved to the next box to the right. Now this loop will terminate until is call less than 15 will become false. That means that it already reached the end of the number of columns, and the program will set call equal to 0 and will add 1 to the value of row. This means that it moved to the next row already. Then again, it checks if the row value is less than 15. Now, these loops will repeat themselves until is row less than 15 will become false. This means that the program has already checked all of the boxes in the 15 by 15 matrix and will return to the main module. And once again, the microcontroller will check if the device is connected to the phone via Bluetooth, and if it's true, it will go back to ScanMat, and if it's false, the program will end.
The following program flowchart was used as the reference of the overall structure and behavior of the mobile application. With that, the detailed behavior of the program when connectivity issues persist was based on this program flowchart. If no problems exist with connectivity, this procedure is followed instead. Given the overall process of the program from the previous slides, the user interface was developed. Shown here is where the implementation was based on. While developing, a more readable system error message was also created, together with a recurring reminder for the user to readjust the position of the child. As presented from this table, several design constraints were encountered during the development phase of the design. These design constraints are economical, social, manufacturability, sustainability, health and safety, ethical, and lastly, environmental. Each evaluation criterion was accounted for these constraints through equivalent values of score and weight. Based on the calculations shown on the matrix table, the most critical constraints are economic, sustainability, and social, with the first two affecting the pressure sensing system the most, while the last affecting mobility the most. Given these most crucial constraints on these two elements of the design, trade-offs were addressed in each constraint. For each of these multiple design constraints, two alternative solutions were considered and analyzed. For the pressure evaluation, the price, the sensor's accuracy, and its wear and tear were the primary factors for identifying solutions. On the other hand, the bulkiness and the dependency of the device to other equipment were the factors. The two solutions compared when considering the economic constraints are using velostat and using a thin film resistor as a primary material in measuring the pressure applied on the cushion. Velostat was chosen primarily because of its lower price and higher accuracy. Next, when considering the sustainability constraints, the two solutions identified are using velostat or using an electrostatically discharged foam. Velostat was still the primary choice because it is more durable in the long term. Lastly, when considering the social constraint on mobility, using lead-acid battery or using lithium-ion battery were the primary solutions compared. In this last constraint, lithium-ion batteries were much preferred because of it is more efficient and it is easily rechargeable.
Next, we have the testing, presentation, and interpretation of data. In this part, we conducted 3 tests in order to increase the reliability of our device. The first test we conducted is the velostats properties test. Before any planning could be done, the velostats properties were first tested and measured to determine the dynamic range of its resistance in varying known weights. Since velostats can have different properties depending on the manufacturer. For reference, the velostat used in this test has a dimension of 30 millimeters squared, and through this test we would be able to know the dynamic range of our velostat. Using an improvised velostat testing fixture, composed of two sheets of copper attached to a non-inductive surface, we were able to create a crude setup for this test. A multimeter is used to measure the resistance of the velostat. After creating the fixture, we used a coin bundle with individual weights of 240 grams, and a velostat is known to provide a more accurate reading for small weights like what is shown on the picture. This would provide us with data for greater understanding of our velostat. The known weights were stacked on top of the fixture, increasing each trial by 240 grams. So this step was repeated until there is enough data to graph the resistance of the velostat in varying weight values. The data we obtained was tabulated as seen on Table 4.1, and these values were visualized on the right picture. The resulting graph displayed a decaying curve in which resistance decreases as weight increases. One conclusion was that weight is one of the constraints of the device. The next test that we've conducted is the graph test using the processing IDE. Using the actual seat cushion of our device with a 12-inch square dimension, we would determine if data could be obtained from the velostat onto the microcontroller through the 16-channel analog multiplexer. The accuracy of the device would also be known in these tests. We connected the device to our laptop through a serial COM cable and uploaded our code via the processing IDE. There should be a generated pressure map that would pop up on a new window. Known weights were placed onto the cushion and the graph seen on Figure A is generated. The window displayed the pressure experienced in the seat cushion. And similarly, a generated value of resistance were also generated on the console, and the weight used on this test is a 2.3 pound weight disc. Table 4.2 shows the values obtained in the experiment, resulting to Figure 4.5. Voltage and calculated resistance were calculated using the formula on Figure 3.8 on our paper. The actual resistance were obtained using a digital multiplexer connected to the 16-channel multiplexer. The percent error of the mean of calculated and actual resistance resulted to 1.43%, thus giving our device a 98.57% accuracy. The last test focuses on the transmission and connectivity aspect of the whole system with the use of randomized testing in terms of the generated data. The following assumptions were also observed. So for our procedures, we've plugged in the microcontroller device onto a power bank and then launched the mobile application, making sure that the Bluetooth connectivity of both devices were enabled. We've generated a randomly simulated applied force in a specific point of the pressure sensing map, and the resulting graphical result from the mobile application upon transmission of the data point from the microcontroller was observed. We've then recorded the location of the point and the specific RGB values, and thus Table 4.4 was populated. It shows that the expected location generated from the microcontroller and the observed location from the Android device always match. Thus, we can assume that the device generates the pressure map with accurate localizations, and the minimal average percent difference of approximately 0.34% indicates that the use of this visualization accounts for a minimal precision loss in representing the pressure generated grid. Therefore, in conclusion, we have created a pressure sensing seat cushion that will detect the pressure that would indicate that the child needs to change their posture suitably in benefit of Kaisaka Incorporated. And the researchers were able to build a seat cushion with 225 sensors using a velostat and copper strips. And the device can read the pressure sensor matrix values and send this data onto a Mega 328B microcontroller. The pressure sensor matrix can be viewed through an application connected via Bluetooth And there were 3 tests conducted to evaluate the functionality of the device, where graph samples were generated to check if the visual representation of the pressure matrix is correct. The data collected on these tests showed that the values generated by the pressure sensing seat cushion was transmitted onto the microcontroller and application with a 98.57% accuracy. That is the end of our presentation. Thank you for listening.